afternoon, everyone. This week we are going to be moving on to chapter 22 over electromagnetic waves. And so in this video, I'm going to talk a little about the first three sections, which is kind of a conceptual introduction to electromagnetic waves and Maxwell's equation and the properties of these waves. So we start with Maxwell's equations, and Maxwell's equations are very important to electromagnetism. And if you ever take any upper level classes, you will do a lot of calculation and analysis involving Maxwell's equations. But since this is an algebra-based class, we're just going to talk about these in a conceptual manner. So Maxwell's first law is essentially Gauss's law, and it relates electric field to electric charge. Okay. Law number 2 states basically that there are no magnetic charges. And what we mean by this is magnetic monopoles. Okay. So remember we said that all magnets are dipoles. They have a north and a south pole. So no magnetic monopoles have been found to exist, and this is a specific consequence of Maxwell's second law. Maxwell's third law conceptually states that a changing electric field produces a magnetic field. And Maxwell's fourth law said a magnetic field is produced by an electric current or also by a changing electric field. So 3 and 4 are kind of the converse of each other. Now, we're not going to do any computation with these, but I'm going to give you an idea of the mathematical form of Maxwell's equations. Okay, so remember, the first law is that relates electric field to charge. The second one has to do with the properties of the magnetic field, and a consequence is there's no magnetic monopoles. Third, changing magnetic field produces an electric field. And for the converse of that, that a moving electric charges or a changing electric field will produce a magnetic field. Okay. The only thing I want to say about flux, we talked quite a bit about magnetic flux in the last chapter. Know that Gauss's law relates, Ampere's law relates to the flux through the electric flux through the surface. So you can think of this as the number, how much electric field is piercing a surface. And you can look at that as the same way we did with magnetic fields. So what I wanted to focus on for this video is the production of electromagnetic waves. Okay. And so an electromagnetic wave is a propagating transverse wave consisting of electric and magnetic fields that are perpendicular to one another. And the general direction that the whole wave itself travels is perpendicular to both the magnetic field direction and the electric field directions. So this is better explained by visuals. So your book goes through this little demonstration, a series of graphics on the production of electromagnetic waves using current, oscillating current. Now, remember, current is made up of charges, right? Moving charges. And the important thing to note here is that these are oscillating charges. So remember, we talked about alternating current. And so if we flip the polarity of current, the direction on a particular time scale, then that causes the charges or the electrons within the wires to kind of oscillate back and forth. So when we talk about these series of graphics, we're talking about the oscillation of the charges within the wires. Okay, so what this is trying to tell you is if you have oscillating current within these wires, then there's a magnetic field that, of course, is going to be produced in concentric circles around the wire. But when the direction of the current constantly changes, that the direction of that magnetic field is going to flip, right? So we talked about if you look at a current top-down view, right, you're either going to have a magnetic field that goes clockwise or counterclockwise. Okay, the direction of that current changes, you flip from, in this particular orientation shown on the slide, then you're going to flip from out of the page to into the page. Okay, these red arrows are representing the electric field. Now, remember, as we move farther out from the wire, both the magnetic field and the electric field get weaker, okay? So eventually, this creates waves, okay? Well, this creates waves, and this kind of spreading out of these waves, after the waves travel far enough, you get electric fields lines that are parallel to one another, right? And then you still have this alternating magnetic field, okay? And the direction of the current is alternating as well. Personally, I don't care for the way that your textbook explains this. I think it's a little easier to understand if you look at what's happening with the individual particles, okay? So if you remember way back from chapter 16 or 17, when we talked about the electric field of point charges. Remember, if we have a positive point charge, then the electric field radiates outward from that point charge in all directions, okay? And the electric field strength is equal to K times the charge over R squared, where R is the distance from the source of charge of the electric field to a particular point. Okay, so that means that the farther you move out from this, the weaker the electric field becomes. Okay, now this graphic is for a stationary charge. So what if we moved this charge, okay? So what if we oscillated this charge back and forth? And this is essentially what is happening in an alternating current. And in the previous graphic where they were talking about, if you imagine the current is being made up of lots of little individual point charges, if those charges are moving back and forth, then the strength of the magnetic field at a particular point is going to change, okay? So what would this look like? Well, okay, let me start this over. Okay, so if we have a static charge here, stationary, that is not moving, our electric field is going to go radially outward like we were discussing. However, if we oscillate this charge back and forth, then this electric field is going to form waves, okay? And these waves are going to propagate. Now, recall also that when we have a moving charge, a magnetic field is also generated, okay? So the magnetic field is going to be perpendicular to the electric field. And so what is produced is these electromagnetic waves that are propagating out into space, okay? So if I follow a point along one of these, say I follow this crest here, right? This wave travels out into space in a direction that is, the propagation direction is also perpendicular to both the electric field and the magnetic field. Now, since every type of matter and everything that makes up matter in the universe, even your own body, contains moving charges, okay? So this means that everything produces electromagnetic waves. Now, the energy of these waves will vary. The wavelength, which we will discuss in a moment, will vary in frequency. But every object produces electromagnetic waves. So let's talk about, well, first let's look at what we were talking about. This is the structure of an electromagnetic wave, okay? As you can see, the electric field is perpendicular to the magnetic field, and the whole wave is moving in a direction that is perpendicular to both of those, right? And this is what we call propagation. Right? So if we follow a particular point here, we'll see that we are moving in this direction, okay? But if we look at the electric field and magnetic field strength at a particular point, as this wave moves, then the electric and magnetic field strength increases and decreases, okay? And it does so in the form of a sine wave, okay? Or a sinusoidal function. Here's another graphic. Okay. So electromagnetic waves move at the speed of light, and Maxwell determined this, and you may recognize epsilon naught and mu naught from individual chapters over electricity and magnetism. But the speed of light is equal to 1 over the square root of epsilon naught times mu naught, right? And so the speed of light is constant in a vacuum, okay? So of course, we will get into this in a little more detail in the next chapter, but the speed of light can slow down in certain materials, but moving through space itself, the speed of light is constant at 3 times 10 to the 8 meters per second. So properties of electromagnetic waves, okay? This follows a sinusoidal function format, and important properties, we have wavelength that is represented by lambda. And so the amplitude refers to the distance of the peaks, okay, the peaks and troughs. A trough, of course, is the negative side, right? So kind of the negative peak. Some of these properties your book talks about, some of them they don't. But a node is a place where that particular, the wave is 0, okay? And so the x-axis represents the direction of travel, the direction of propagation of the wave. And waves are transverse, meaning E, electric field and magnetic field are perpendicular and perpendicular to the direction of propagation. Another important property, electromagnetic waves do not need a medium in which to travel. Now, other types of wave, such as sound waves, do need a medium in which to travel. That's because they travel by essentially moving particles in the atmosphere. So sound waves cannot travel in a vacuum. Electromagnetic waves can, okay? And we can have any frequency and so the frequency and wavelength of a magnetic wave multiplied is equal to the speed of light. And before we finish up, let's talk about electromagnetic waves and the electromagnetic spectrum. Now, we classify electromagnetic waves into categories according to their wavelength and frequency. Now, this area here represents all visible light, and that's light we can see. So all of the light from the sun that allows us to see everything around us falls into this very small range, okay? And at above that, you have UV light, X-rays, gamma rays. Now, these on this end of the spectrum are what we call ionizing radiation. Now, as we move from the left to right up the spectrum, energy increases. Okay, so smaller wavelength corresponds to more energy. And I believe there. All right, so let's look at it this way. So as you move across this spectrum from left to right, you have decreasing wavelength and increasing frequency. So greater energy corresponds to greater frequency, but less wavelength. And if you think about this as kind of oscillations, so if you think about something, particles that are oscillating really, really quickly, then they're going to, like we saw in the simulation, they require more energy, and then they're going to produce wavelengths that are closer together, right? Because you have more oscillations. So that's a good way to remember conceptually that shorter wavelengths have higher frequencies. Now, on the lower end of the spectrum, we have infrared, microwaves, radio waves. And the most common question, because the language can get a little confused, is most common misconception that people have is that radio waves are sound waves. Radio waves are not sound waves. Radio waves are electromagnetic waves. Okay. So I will wrap up. That's everything for this video. In class in our Zoom meeting on Thursday, we will go through sections, finish up with 22.3 and go through 22.4 and 22.5, right? And we will get into the math involved in this chapter. So that will conclude chapter 22 for us this week, and then next week we'll move on to chapter 23. I will see you guys in our Zoom meeting.